All right. Good afternoon, everyone. Welcome to MCC for what looks like it's going to be certainly the highest moisture content of anything here at the conference. We have Stephen Heminger. He's a Linux developer who specializes in kernel networking issues. Please welcome him.
Daddy, the internet is slow today. That's what Jim Geddes' teenager told him. And he did what any parent would do. He told him to shut up and go away. No, he didn't. He actually investigated why it was slow. And this talk is going to talk about it in both a technical and a kind of fun way. So you're going to have to wait around a little bit till we get to the fun. First off, Jim Geddes coined the word bufferbloat. The definition of bufferbloat is the internet slowness you see because of excess queuing. And this can be a rather extreme phenomenon. I like pipes and plumbing. It's something I've started. But basic queuing theory. Yeah, we're in a university. We have to do some math. If you look at a network, and this is the utilization at the bottom, so 100% over here. It's empty over there. And how much delay you experience is a function of how busy it is. You kind of know this when you go to the store, and you go to the store before Christmas, and you're going to buy something, and everybody's there, and you have to wait an hour. The green line here is an old, slow T1 line. This turns out with modern, fast networks, you get this knee. It looks like you're fine, and all of a sudden, it's off the graph. The two things to observe is this graph goes to infinity when you hit 100%. So if something actually uses all the network, you're going to have to wait forever. Why would it matter? Well, there's some basic services that have some basic timeout values. If you have a phone call, a delay round trip of longer than 10 milliseconds, the phone call ends with VoIP. Or you don't want to talk to that person because you're totally confused. If you're using a mouse over a desktop, remote desktop, or any video game, 20 milliseconds is about the maximum lag you can stand before you want to scream. Around 100 milliseconds, if you're using a web browser, DNS lookups start to fail and you start to get web browsers locking up. Somewhere in the middle there, ARP and network discovery, the things that do address resolution, timeouts start to occur. About a second, most users give up and start reloading web pages and making the world worse. And there was actually an incident, John Corbett, who writes for LWN. At one point at a hotel, he wrote a short article. He SCP'd it up to his website, and it wouldn't go through because there was enough buffering in the hotel network that it would fill in the buffer, instantly go out. SCP is a really smart program. It waits for the response, acknowledgement from the other end of the application that it actually got uploaded, and it timed out after 5 seconds. If article was still sitting in the hotel queue waiting to make it through. So applications start to fail over a second. And at some point, DHCP fails and your machine falls off the network. I think we're all familiar with this from being at conferences. And what are the things that can kill you on this? And it turns out there's tons of applications. All the applications that basically do any upload traffic or any application that monopolizes the link going down. So it's not very hard to make something that totally breaks the internet. There's a group at Berkeley at the ISC Internet Test Lab that has this tool called Netalyzer. And you can use it, and I'll show you an example at the end. And it gives you a report, and they basically collect data from everybody who runs this tool. So every dot is somebody who ran the tool. And over here is how much buffer capacity was on the network. And over here was the bandwidth that they measured. So somebody up here had a really good, like my house, 25 megabit connection. I guess in the States we're kind of poor. I think you're better off than that. But then the green line is half a second, yellow is 1 second, red is 2 seconds, and black is 4 seconds. And you start to see that there's many seconds of buffering on the average person's network connection. By the way, you may wonder why this region is all white. The people who wrote the tool did not actually believe there would be anything that bad, and so they threw those data points away. And in the upload direction, they had the same thing. Now, this is a rather fuzzy graph, so I thought I'd insert Jim Getty's demonstration of this in a YouTube video.
My service is typical for today's broadband service, and I have over 1 second of delay. To demonstrate Bufferbloat, we'll use Google Search, which is carefully optimized for speed, using a typical broadband connection, as shown by the ICSI Nettalyzer data. We will run 3 tests. During the first test, we just run the benchmark on a completely idle connection. As you can see, the benchmark runs very fast, visiting Google Search 5 times. The results are on the screen. The second and third tests add a single file copy upstream to the identical benchmark, which is downloading web pages. How fast do you expect this test to run? Just as fast? Half as fast? I let the copy run for 10 to 20 seconds to both fill the buffers and to overcome any speed boost that the ISP may give me, such as Comcast does with Power Boost. The file copy is from my laptop to a server on the internet. This operation is just like uploading a video to YouTube or Vimeo. Sending an email with large images attached or a video attached is another example. A third example might be backing up your files for remote backup service. With that single competing outbound copy, you can see Google performance is now glacial, through no fault of Google. You might have predicted that performance should be nearly as fast as the first test, but it's not. It's radically slower. Even experts often overlook the damage to downloading caused by filling the bloated buffers in the upstream direction. Trying to use VoIP over this link is like talking to someone halfway to the moon. This really is, the internet is slow today, Daddy, as my family kept telling me. As you'll see from the benchmark results shortly on the screen, the 5 visits to Google Search now take 10 to 15 times longer than they did during the first test. For the third test, we'll insert an artificial bottleneck that has little buffering by using the so-called QoS features of many home routers, moving the bottleneck from the bloated broadband link into a location in the home router with little buffering. To ensure that the bloated buffers in the broadband link never fill, I am setting the bandwidth to 70% of the ISP's provisioned speed. We run the benchmark again while the file copy continues. We are now close to the speed of the first test, despite the bandwidth reduction and the simultaneous copy, achieving performance about what you might have originally predicted, or maybe even better performance given the bandwidth reduction and the copy. The internet is slow today phenomena is gone. Reducing our bandwidth by 40% sped up the service under load by a factor of 10. Anyone using a link can destroy performance for themselves or for anyone also using that link when it's the bottleneck link. Remember, this demonstration was on a link of typical Bufferbloat. Bandwidth and speed are only vaguely related, as Stuart Cheshire explains in It's the Latency, Stupid. Which internet service would you prefer to share with your family or use at a hotel or a conference? One with Bufferbloat or a service of the same bandwidth without Bufferbloat? I think this demonstration makes it very clear.
So the first thing we started to see was Bufferbloat. And one thing you have to understand that's causing it is the TCP protocol that's underneath. And I actually was working on this 7 years ago when I was here at LCA the first time. So you have to understand the classic TCP is adapting to the network it sees. So the way it works is it starts out at a slow speed and it ramps up, kind of like you took off from a stoplight in a drag race. And then at some point, it goes too fast for the capacity of the network. Packets get dropped, it resets, and it adapts back to half of the last value it saw. And it basically has this sawtooth function where it's adapting to changes in network speed. You have to remember, this was built for back in the early days of the internet or pre-internet with ARPANET, very slow connections, things would reroute. It's totally adaptable and totally able to deal with changes in speed. But TCP starts to get sick when you give it way too much buffering. This is an example of a healthy graph. Stanford CS244 had an assignment to use the mininet in the EC2 cloud to demonstrate buffer bloat. And this is the result from, I got the best result assignment yesterday. This is what it looks like normally. This is healthy. TCP is adapting. It's going up and down. And the bottom is how long time a ping takes. And it's healthily staying at a reasonable 50 millisecond layer. Given the EC2 cloud, that's fairly healthy. Here we went from, the other one had a queue of 6. This is a queue of 100 packets. All of a sudden TCP thinks it's got a really, really fast network and it's ramping up. And then it comes crashing back. And then its functions get really long. And the round trip time, in this case, goes up to almost a second. So, totally unusable connection results. And the people who designed TCP were worrying about this area of the design. So this is the TCP window going up, and this is how much throughput you get. So they were designing for this healthy region. And buffer bloat, turns out, puts you off in this cliff region. And in fact, it can get so bad that TCP timers start to adapt seeing these huge queues, and they start to think they're going to the moon. And they won't retransmit, and they get even worse. So the problem gets even worse as the tail gets even longer. So what do users do? This is a Linux problem, right? Blame Linux. Well, that's kind of true, but other people work. Actually, Mac OS has the same problem. Maybe. Windows XP. Windows XP is really old. Windows XP does not support TCP window scaling. You have a maximum outstanding data of 64K, which means on a reasonable internet backbone, you get a maximum of 8 megabits a second. You can't go over that. So because they're so old, they're rate limited 8 megabits a second. Windows 7, they wanted to support media playing. They were testing. They discovered that basically they ran into the Bufferbloat problem, didn't investigate it any further, and basically rate limited every Windows 7 desktop machine to 80 megabits. So it's kind of like it's like having a teenager in your car. You want to have it max speed at 50 miles an hour. It turns out that the Android guys discovered the same problem running over 3G networks. So they did some Linux tuning to reduce the receive window down. So Android's phones have a hard receive buffer limit to basically do the same thing as the other OSs. So basically, people put in hard governors to work around the problem. ISPs. I don't know if you got this here, but in the States there was a brief period where every ISP was talking about limiting BitTorrent, net neutrality blew up and everything. And Jim contacted people at Comcast and they said, no, we're really wanting to do this because we're getting customer support calls because the internet is too slow. And they basically were finger pointing back at the customer saying, what you're doing is making our internet slow, or your internet slow, stop doing it. And it was their way of restricting applications, was their way of limiting to solve the problem. Now we get to the fun part. In order to understand what that QoS thing Jim was doing is, I wanted a real physical hands-on demo. So to do that, that's why I've got all these tools. We'll start out with, I have a volunteer, Rachel. We'll demonstrate the basic reason we have queues at all. Oh, we'll go Jumbotron on this. You might need to just twist the camera to, I can stand here. We basically try to pour that water into that hook.
Thanks too.
You go, come on, go faster. Doesn't work very well, does it? So in networking, we use queues. It's a little easier, isn't it? It's no real problem at all. Basically, without queues, you can't go from one speed to another speed without dropping data in massive amounts. So you may think a little Q like that is good. Maybe a little bigger Q. You can pour that one. Well, you know, if a little Q is good, why don't we go with an even bigger Q? After all, memory's cheap. We'll go with a really big Q. Just pour it all in there. Go ahead, pour it all in there. We'll do that download. Go ahead, put your download in there. We'll have some more. Oh, what about my little VoIP packet? And maybe it's going to come. Oh, I made it there. I didn't have enough water in there to do. I normally make it over the top. But you know, you're playing a video game. You want to kill an alien. You want to buy that cat salt shaker you saw on eBay. You can't. The teenager's busy doing Netflix. I mean, it just doesn't work. So you may think that Linux is kind of. If you look inside Linux today, you'll find this. This is what you get by default. Priority FIFO. We have 3 models. We have regular, jumbo, and we have the really high priority stuff. And it works, except almost all of your traffic ends up going in one bottle. Doesn't really work very well. There's very few things that ever use the other bottles. And overall, this doesn't scale very well. You can't even use it outside your machine because the decision to do which bottle is based on the application deciding to tag which packets. So once I go outside this machine, my ISP is going to go, everything's the same, I'm putting it in one bottle. So this was a reasonable idea, but it depended on somebody choosing the right bottle, and not only that, that there's enough bottles that traffic will disperse. Not only that, there's the other problem. If something decided to go in the high priority queue, the other ones are totally starved. So in the Windows world, somebody would make an application that increases your download speed. Always goes with the same DSCP marking. Internet researchers were not oblivious to this problem. Van Jacobson invented something called RED. Now RED is not just a bottle of stuff. RED is a queue where you decide if things are getting backed up, that there's holes in this bottle, that things should squirt out. I don't know if you can see it, but things start. And the farther it gets up, the more things squirt out. And that was a great idea. There's only one problem. Building this bottle is really hard. Because where you want to put the holes, and how many holes, and how far up you put the holes, is a function of the speeds and how much is coming in. And Van Jacobson actually loved the analogy of plumbing. He still does. He wrote a paper called On the Problems of RED. And in the paper, he put a picture of a toilet. The reviewer said this is inappropriate, and it never got published. So actually, the ways to fix RED never got published because of plumbing. So every time we bring Bufferbloat up to the enterprise folks, they say, we're smart. We have smart water. They do carefully controlled hierarchical queuing. They break things into different traffic. Here's my Oracle traffic, and here's my backup traffic. And we have careful little dials which we adjust the rate of each one. You know, this works great in an enterprise. It doesn't work if you're an ISP. It doesn't work if you're just trying to do a desktop. So this may be a perfect solution if you want to pay an admin. Or the hacker go run Wondershaper or one of the scripts that sets this up. But it really isn't going to solve the general thing, which is we want a one-size-fits-all, works for any speed, and any user can use it. White shirt. So Paul McKinney who is not here right now because he's in the other talk, and some other people invented something called stochastic fair queuing. Now, with stochastic fair queuing, they have 128 bottles, but I couldn't fit that many in. And the idea is that you take a random hash of the flow, and you choose the bottle you want to go in. And the next flow comes along, so Jim's upload is in one, and his son's could be in another, and somebody else is in another, and they all share very well. And it's unlike this other one with the bottles, nobody had to set it up. We're using the magic of hashing to give each flow their own private queue. And this works pretty well, and as we'll see later, it's the basis for some of the later things that have gone on. But more advanced things have happened. You may have seen recent work in something called CODL, or controlled delay. And let me make sure this is off. And the idea behind CODL is all these other ones work by adapting at the bottom. But CODL says, look, if something's been in there 5 milliseconds, it's old. It's kind of like at the grocery store. You don't want the old milk. You dump it out. You wait till you get to the good stuff again, and then you close it back up again. And with that, you guarantee that where's 5 milliseconds come from? Remember that VoIP number, 10 milliseconds? We guarantee that VoIP will still keep working, no matter whether this is a big fat internet connection or a really slow ISDN connection somewhere. It works no matter which. We always guarantee 5 milliseconds. And this proved to be pretty much the best solution we have until Eric Dumazet and a few other people got the other idea of combining CODL with SFQ, but I didn't have the time to make that. So just imagine that every one of these is one of these. So you have hashing and you have the control delay. So if you happen to hash collide with somebody else, you're still going to get that 5 millisecond guaranteed delay. There's one last problem which occurs, and this one takes a little more setup. There's a situation where it turns out these buffers stack. And you can pretty much, when you actually look inside Linux, you'll see that there's queuing going on everywhere. And only the best for it. What happens is, it's important that the bottleneck that occurs is somewhere where you care about and you have control. Because it turns out there's bottlenecks at the queues at the socket layer. There's queues where we have intentional policy, the queuing disciplines. And then there's big queues off in the network connections as well, the network drivers. So we've worked to add some additional features that help in the recent kernels. One is the network drivers have byte queue limits that try to keep the amount of queuing at the network driver small. The other one that Google and Eric have worked on is TCP small queues, which works from the top to bottom. Since we're on one system, we say we won't pour data into the top, out of the socket buffer, faster than it's making out the bottom. And because of this, we get an end-to-end systemic thing where one socket cannot actually saturate any of the other queues below. With that, I'll try to dry out at this point. Oh no, what to say, buddy? Oh well. Yeah. All this fun with plumbing. Yes.
Are there also hardware queues where packets are getting delayed that we can't do anything about?
Well,
like they're on the card?
There are a few in some of the wireless cards, but
the idea behind the byte queue limits is, for example, the 10 gig read buffers. We make them big, but we only use a small part of them. And we sort of limit, it's dynamic clocking. So as data goes out, we can, oh, it's going fast enough. It actually got empty. We can have a little bit of queue. The danger with all these plumbing analogies is what works with water may not work with packets. So I'd like to show you some recent results of what has happened. Holland, I can't pronounce his name, Jorgensen, did a test. This is a live test on real data, on real network connections. This is a graph showing extreme buffer bloat using FIFO. He's got an upload and a download, and there are 10 megabit upload and a kind of 10 megabit download, and his ping time goes up to 1 second. A human wouldn't put up with a 1 second response. Using stochastic fair queues, the multi-bottle thing, his 10 megabit upload and download were consistent, and the ping time was consistent. And the reason that happens is basically the upload and the download and the ping all basically get their own bottle. So each one's got their own separate slice of the network. The control delay, the one with the valve, gets a similar kind of response, but the ping starts to take a little longer at the front. And that's basically where Coddle is actually deciding that it's gotten full and it's going to have to start dumping things. So there is a bit of adaptation period at the start. The FQ Coddle, which is the combination of fair queuing, the bottles, and the valve, gives the best results and it's the most stable. And this is currently the best of breed of what we have in the upstream kernel. So, now you've seen all this, what do I think you ought to do? I really would like people to help out and do things and try and give results and give data. And I'll show you some things you can do as individuals or as developers to try to help out with this project. The first thing is, I didn't put the URL down because you're all googly talented in here. You run the ISC Analyzer, and it gives you a report about all these things like your DNS is totally screwed up and all these other interesting things. But one section in here, it basically tells you how bad you've got. This was running over from the dorm yesterday, 490 milliseconds of buffering. And if you run that, and you run it in various connections, you can just see how bad you are where you are at any time. And this is actually better than most of the other benchmarks. The problem with most benchmarks is most people run things like netperf or iperf that do a single connection, nothing else is there, and never measure latency. Or they measure a ping, and there's no other traffic present. It's kind of like measuring an engine sitting in a stand. The other one is there's the Bufferbloat project. We have mailing lists, we have people involved, we have people discussing ideas. And if you're a developer and you're interested, you want to go help out, you want to go try things, you want to look at other people's data, that's where most of this came from, was people on the Bufferbloat project giving ideas. Lastly, if you're a home user and you're willing to spend a little money, that we have a version of OpenWRT that runs on a Netgear router, pretty modern 1 gig Wi-Fi router, and it has all the new Q disciplines in there, and they're enabled by default. And you can even go in there and fiddle and measure. And if I actually went to the trouble, said, I'm going to give this talk, I probably should go set this up. And I actually noticed the definite improvement in my house with the FiOS, and there's only 2 of us, but it's enough to make it better. Where are we going from here? As you saw with the multiple bottle thing, there's a systemic problem. It's not just buffers in one place. So we can do as best we can in one place, but we need to have a more systemic view of the operating system and what's going on. For example, the FQ Coddle really should be saying, I'm going to guarantee that the worst case delay for a packet going through the system from top to bottom is 5 milliseconds, not 5 milliseconds in that subsection. And there's various ideas on how to do it. As always, details are in the implementation and how to make that happen. I think we're far enough along that we need to change the default Linux queue discipline from the old multi-bottle to something else. We're probably about 6 months away from deciding that something is stable enough to just let it in the back and just have it when he does the next build. I don't know, maybe you do it now by default. But the point is that no distro, and most users are not going to go to the trouble of setting this up except on their own network hardware. So we want the default that people get out of the box to work right. And we're to that point where we're ready to do that. Wireless actually proves to be a much harder problem than all these simple things we talked about. Wireless has things like aggregation, speed changes. Different speeds occur on wireless when you do multicast and when you do unicast. And it doesn't say that the assumptions and the solutions we made are wrong and won't work on wireless. It's just that better solutions are needed to make wireless work really well. And lastly, all this assumes a certain amount of infrastructure that may start to rattle apart at 10 gig and 40 gig. At the super high speeds, measuring times of packets, accessing the clocks takes too long. So we have to figure out how to do more self-clocking things or measure end packets or something else to try to have better algorithms that work at these super high speeds. With that, I thank you for your time, and I hope everybody stayed dry, and we have time for a few questions.
Thank you. Thanks. That was great. I just wanted to ask. Okay, the obvious question is, how you've set up OpenWRT with these settings. So how can I set those settings up? Just.
It's not a standard OpenWRT.
No, I understand.
Serial WRT.
My router runs it in.
If you take Serial WRT and you go to the Bufferbloat wiki, I think actually if you install the image and you get the default setup, it's on. And with Serial WRT, there's more menus that you can go fiddle around.
My router just runs plain old Fedora 18.
The software for the more advanced stuff isn't in there, but the two things you can do on almost any router is you can lie to it and say its upstream bandwidth is lower, and you can run something like SFQ that's been around for 10 years.
Okay, thank you.
And I think even OpenWRT by default has that.
So everything I've read about Bufferbloat has pretty much the problem isn't at your home connection, it's out in the entire internet.
That's sort of true. It turns out that the worst problem is probably in, let me use my example in my house. I have 1 gig all over the house, goes into now the Netgear wireless router, and now it goes into a FiOS, what is Linux-based, was my old router, out to FiOS. Your cable access box, your FiOS access box probably runs Linux, probably has a huge amount of queuing in it by default.
You still have your ISP.
And your ISP may have a big queue at the other end. What you can do is you try to reduce your rates. So remember with the bottles, if the queue above is slower than the one below, so if this queue is slow, so it's got a small host, by the way, these bottles have been modified a little bit. This one has got a bigger hole. Nothing will ever build up in this one. It will only build up in this one.
The thing is, you need a queue on every home connection. So other people who don't have this kind of stuff might end up taking some of the bandwidth.
It's true, but at the ISP and the backplane level, it's much less of an issue.
I see.
I mean,
better troops.
Yeah, I'm in ISP. We don't have any trouble in our backbone because the speeds are so high that we can't fit in enough memory physically to get anywhere near a buffering problem, let alone a buffer problem. The problem for us is in the transition from the backbone to the customer, and in that transition, there's a lot of DSLAMs, a lot of FiOS stuff, and there's also a lot of Linux, right? Running what we call mid boxes, right? And if you fix the problem for Linux, for people's desktops, you will fix the problem for all of those firewalls.
Yeah, that's
all
the
those
other thing,
traffic
is I don't
shapers,
expect
all
the
of those.
my FiOS box to ever be fixed. But I expect that whatever vendor gets something from Taiwan and it shows up in the next generation of networking appliance, that it will be fixed.
Yeah, I don't think it will be fixed in the DSEMs. We've had a look at the DSEM used by an ISP we cooperate with. I think that's we're helping configuring their equipment. And there isn't enough nerd knobs, ironically, in Cisco iOS, which is full of nerd knobs, to really address the problem. But we expect further down the track for those knobs to appear, and then for the more clueful of the ISPs to apply them.
One other good thing is Van Jacobson and Kathy Nichols, who did the coddle stuff, intentionally did two things. One, they published a paper rather than having a patent made. So it's now a published prior art that anybody can build, proprietary Cisco can build it, or we can build it open source in Linux.
Yeah.
So it's like the best public domain solution.
You're looking at a 4 to 5 year delay before that appears in the hardware we use, simply because that has to be translated into a silicon thing, and silicon issues are about power and clocks and stuff like that. And for Codel, even running a clock against each packet, you're talking a lot of power. And so smart people have to work through the silicon, and then there'll be something that approximates Codel, efficiently implemented in hardware that ends in the equipment.
A lot of the tractable parts of this problem are between rate adaptive transport protocols, which is variants of the TCP flow control algorithm, and the queuing infrastructure inside the network. UDP, you have no hope, right?
Well,
Within streams at 10 gigs and you've got a 1 gig pipe, it's going to spew packets everywhere, and that's just the way it works. It's insensitive.
Well, no, but I mean, if you look at the coddle example, if I had somebody spewing a video and they were stuffing it, I would just dump it to the...
No, okay, that wasn't the point of the question. So I wasn't really talking about mixing sensitive and insensitive application. I was getting into the TCP part of this. Because these days the world isn't just all Reno coloured, is it? You know, there are variations of fast, there are variations of cubic, bicubic, there are all kinds of flow control algorithms that are trying to second guess the queuing behaviour of the network.
Actually,
well, that's what they're trying to do, because they're trying to optimise their responsiveness and throughput against the actual dynamic behaviour of the network. So TCPs are actually trying to adapt to what they sense of the network. And you're now saying it's time to change the queuing behaviour. How do we control the total system when we've got so many variables at play now?
We've actually found in testing that the two play well together. In fact, Van Jacobson says he wished he invented Qubit because it was more complicated than what he was ready to do when he invented the initial one. And it turns out Qubit responds very well to any of these things. Basically, any TCP wants feedback like a child right away.
Oh, right, it's an act control feedback.
So basically, the faster you can dump packets to tell it it's overloaded, the more it can adapt. So the
to some extent, but if you start using stochastic pair queuing, for example, the responsiveness of individual flows is actually a lot lower. The amount of rate they can increase when there is slack capacity is actually impaired, because what you've got is a system that's responsive to injection of small uncontrolled packets. And this then gets into the really interesting question: what are you trying to engineer the network to do? Because one way I can make big flows go really well, and VoIP just disappears from the planet.
It turns out that with this, I intentionally chose small bottles. You want lots of small bottles to make it work. If you use lots of really big bottles, you just end up with the same problem again.
Well, they might as well not be there if that's the case, yes.
So that's part of the reason it works, is because these are small, and so the individual flows get their feedback fast.
But equally, their adaptability when you change the number of flows is a lot slower. And this is the trade-off that happens when most of us try and design the queuing behaviour in the transit networks. There's a really hard decision about what are you trying to do with the network and which sort of objectives you're trying to engineer for. Most of us, when voiced with this, looked at the amount of money we got from VoIP and said, oh, bugger it. Because quite frankly, you know, spending 95 cents
and you raised another issue, which is actually applications have started to adapt to bad behavior.
Right.
If you know how Netflix sends data, they send it in 10-second chunks. they could stream it at the rate of your video, but the network is not stable enough for them to do that. So they send you in 10-second chunks, because that will work, and the world can clear up in 10 seconds, and you'll never notice the video's full.
What's the uptake on ECM and similar, and is that usable at this point as a means of conveying congestion rather than dropping packets? Is that basically dead, or?
The ECN had two problems. ECN is basically a feedback mechanism that, unfortunately, there was two things. There was ancient equipment that would just break if you had ever received ECN. That appears to be gone. But because of that, the amount of equipment in the real world that drops it is pretty high. And so in a lab you can do it, in a campus you might be able to do it, but in the wide world of the internet it really isn't that effective.
Much better.
All right, if we've got no more questions from the audience, everyone join me in thanks Stephen for
my volunteer.
if anyone wants to help clean up.